right, so let's continue with the second lecture by Nikita. So I forgot to mention that you probably go to one of the best possible high school mathematics education in the world. That's why he's so good in math. He went to the famous 57 school in Moscow. This is a school which, well, maybe Maxim has different opinion.
Now it's unfortunately my school used to be famous, now it's infamous.
I don't want to go into that right now. So in any case, Nikita is a recipient of many prizes in physics, Hermann Baur Prize, actually in math as well, Compositio Mathematica Prize, and then the Heinemann Prize. So let me write on you for a second lecture, Nikita Nekrasov.
Thank you. So it's very late, so I should first of all I should start with a joke and then maybe make my presentation short. So before I start with the joke, I want to thank the group for organizing this conference because I just realized and confirmed by the previous speaker that we as Stony Brook, we're like French. So what is special about French scientists is that they don't talk to each other unless they go to some conference elsewhere. So the only way to first of all make us meet and then talk to each other. Thank you very much. Thank you very much. No, I learned a lot about my colleagues. The joke is due to Jim Simon. So he used to open his remarks by quoting a cartoon from New Yorker. The guy is about to give a speech, and then there is a chandelier above him, which with a chain which has been snapped, and he says, "Just like that, would be brief." So I don't know how many slides I prepared for the second half, so I might really be brief. So let me start, but just in case I prepared the whiteboard, maybe you will. So if your system has a continuous symmetry, which I will assume is generated by is actually B group, then this C group action on the symplectic manifold, original symplectic manifold, it's going to be Hamiltonian, so it comes with moment map, and that allows me to represent the twisted partition function as a path integral over the loops into my symplectic manifold, but with exponential term dressed with moment. So there's an additional parameter, this partition function, which is the background gauge field for the group gamma. The only role of the gauge field is to generate its monogamy. So that's the group element G, which is the actual parameter function. But now, if everything is real, you can make a change of variables in this integral, and so you can actually get rid of this gauge field by doing what's called gauge transformation. But that would change the periodic boundary conditions and move to the twisted boundary conditions, so that the initial point x of 0 and the final point x of 1 will be related by the action of this origin. It's the equivalent formulation. The advantage of this formulation is that it immediately allows the analytic continuation. I can make a complex, and I can, so I'm still integrating for periodic loops, but now if I try to undo this, the presence of the gauge field by doing complex gauge transformations, I will be forced to go to the complex domain. What I will do. Question. Yes. What is it? Yes. Path order exponential. Oh, this is okay. So if you have a circle and you have a one form, the circle valued in the Lie algebra, you can ask, so this is, it's a gauge field, so you can look for the horizontal sections, this connection from psi, it's a function, the circle with values in some representations of the algebra, maybe the majority. So if you solve this equation with some initial condition, then if you start here, then go all the way. So the value of the solution, as you approach this point from plus 0, 1 minus 0, it's equal to group transformation applied to the initial value. So this group element is denoted by method of exponential. The reason why it's all that is that it's actually there's a formula. It's called iterated integral. Physics is called Dyson series, but mathematicians probably call them Chern integrals. John just wrote the book integrated integrals and something is up. Here, so G is a formula. So G is 1 plus integral A 0 to 1 plus integral the series for exponential, except that instead of the writing 1 over n factorial, you integrate over the configuration space, because here the order is important. What can be? Yes, to make sense of this formula, I really need to think of A as belonging to the universal developing algebra. So associative algebra is supposed to be algebra. Let's see. Okay, so this twist and the background issue can be complexified so it's analytic properties of the function. And this will be exploited now in my main topic, which is the field theory. So now from quantum mechanics, which was 0 plus 1 dimensional field theory, let's go to the 1 plus 1 dimensional. So I will explore 2 examples, which are the single models. This is something we worked on with Igor Krichever. So the single models studying maps. Classical single models are like theories of harmonic maps of Riemann surface to some Riemannian manifold. And I will have only 2 examples of the Riemannian target space, the spheres and the projective space. Now, there are many ways to think about the spheres and projective spaces. So I need to specify the Riemannian structure. I will be talking about the round spheres, the standard British geometric of the projective space. And these are induced from embedding, in case of the sphere, I think of the sphere as embedded into the Euclidean space. So the vector X in the n-dimensional Euclidean vector space, which is subject to the constraint. In the case of the projective space, view the projective space as a portion of the odd-dimensional sphere by the U1 action. This odd-dimensional sphere is embedded in the same way to the vector. So, so the induced metric is as curvature. So if you write it in local coordinates, it might be complicated. So this functional looks complicated in local coordinates, describes interaction field theory. But we can try to simplify life by using this embedding in the vector space. Then we can, this embedding also allows us immediately to complexify. So we will follow the same logic. So we want to deform the contour of path integration away from the real slice of the space of real fields into the complex domain, so that it will pass through critical points. So our goal first is to find those critical points, which may happen in the complex domain. So I need to explain to you what does it mean to complexify the map and map space of maps of a real Riemann surface into the sphere of projected space. So the way I do that, just simply by complexifying the ambient vector space. So with complex sphere, the complexification, the sphere is just a quadric. It's a quadric. C to the n, which is invariant under the action of the group O and C. The only thing I want to stress is that this constraint, this quadric, is it's a holomorphic equation. So it's not like an equation which describes the CPN minus 1. There is no x bar here. It's a conjugate equation for x bar. Similarly, for to define CPN, CPN is already complex manifold, but I need to complexify it. So I first abuse CPN minus 1 as a real manifold, and then complexify. So what I do, I take the complexification of the same things. So I take C to the power 2n, and then perform a syntactic reduction with respect to C star. So I write this equation Z and Z bar, the sum over I C Z bar equals to 1, when Z and Z bar are independent complex numbers. No, they're no longer complex conjugates. It's different notation. Then divide by the C star action, which multiplies Z by a complex number, Z bar by its inverse.
So you're integrating over a Riemann surface.
But I'm integrating on the Riemann surface. So I'm studying the ordinary map. So I have some Riemann surface, so this is real, dimensional. It's as I was taught by Sarnak recently, so I should distinguish Riemann surfaces and Riemann surfaces. So to write this functional, I only need the Riemann surface. Riemann surface means conformal structure. Riemann surface means actual metric. So classically, you don't need the metric, only the conformal structure.
That's your contour. That's your contour.
No. The contour is infinite dimensional. It's the space of the contour. It's the space of maps. Say C infinity of my Riemann surface into the target space. So X is either the sphere or this. This is my initial contour. Now I want to deform it. I want to think of this as sitting inside the space of maps of sigma to what I call the complexification of this. So I just defined what is that.
So it just means something over which you're integrating, moving.
Right, so I'm moving this guy inside this. And I want to, so this was maps, sigma X, then this is sitting inside maps with sigma C. There are some points inside this, in this complexified space, which are the critical points of the analytic continuation of this function. So my contour will somehow decompose the sum of Lefschetz thimbles associated with those points. But I first want to identify those points. Now these are points. This is contour, these are points. critical points of the analytic continuation of S. I will now explain how what
So
causes it.
you said you're going to deform the contour.
Yes,
So what does that have to do with critical?
deform it until
This is the matters, all the space of matters.
right. This is my contour. Then I want to decompose this contour into contours corresponding to Lefschetz thimbles. So in some homology group, I want to say that this is equal to so I want to classify those contours.
The infinite dimensional space.
Yes, it is.
I don't know how to think of that as a homology.
That's why you need me. That's why you need me. I also don't know, but I do.
I know, I mean, I know.
Wait. That's it. So what do you mean? What are we talking about? I'm trying to follow it because I have to have some sense of something to follow.
I'm saying, so pretend this was a finite-dimensional problem. So what would you do in the finite-dimensional problem? In the finite-dimensional problem, you would first classify the critical points of the action.
Why? You're doing an interval.
I need to repeat the first half of the first lecture.
Can I ask a question?
No, I need to answer. Because it's important.
Yeah.
So we are,
What has changed?
so we're studying this integral. We're not interested in contour per se. We're interested in the value of a period.
Yeah.
So this is equal.
Yeah, that doesn't make any sense.
Right.
Because I don't know what homology means.
Let me ask a related question. Sometimes you do this by.
No, I don't want you to ask a question. Just wait till we finish the discussion. We declare it finished and we're in place. How am I supposed to follow the lecture? It doesn't have any fidelity. We have the recipe for interpreting the interval, and the recipe will take nice form, or something like that.
Saying that if the integral existed and had a property which is always assumed in quantum field theory that you can integrate by parts, meaning that even though the space of which you integrate is non-compact, but the integrand decays sufficiently fast at infinity, so you can integrate by parts, and so by that assumption and by assumption of analyticity of my measure, I can deform the contour. Then I'm just following the logic of the first half, where I said that there is a preferred way of deforming the contour. So preferred way.
In your first talk, you were giving the algorithm that interprets questions.
Maybe I ran through the logic too fast. So this is what I was trying to explain. So there's a way to deform the contour so that this integrand gets smaller and smaller. So this way uses the gradient the real particles. So if you continue this flow, you get stuck at the critical point. So my contour will somehow hug those critical points and will hug them in the directions of the steepest descent trajectories. These are Lefschetz thimbles.
So that's basic.
That's the basic. It's not the basic of quantum field theory. Basic quantum field theory, unfortunately, not so far, was based on the case when you know one critical point here on the real slice, and you just expand around this point. So you just approximate your integral by first by Gaussian, and then compute corrections.
Adding another step.
Yes, I'm saying that this was just the first step because there are other critical points. They give competing contribution.
Ready?
These are some infinite cycles. Precisely. Yes, yes. Because this is half-dimensional cycle.
So it's just right.
Yes. And so the local picture, so near the critical point, if the critical point was worse, like it was isolated, then the approximated near it's infinite, of course, but suppose it was finite. So then it just sum of squares. Now, if you look at the real and imaginary parts,
Yeah.
so I want actually yes. So I want the contour to be such that you have only negative x squared, but I don't want positive thing because then it will diverge. So my contour will be y equals to 0 near this point. So, but this is something adapted to the neighborhood of the critical point. So this is y equals to 0. So this is where the contour goes. Go from here to here. That's the whole subject of parabolic differential equation. So this is it's a job for 100,000 people for 100,000 years. I just want to classify the starting points. Those cannot be classified. And what Carlos mentioned was people were trying to extrapolate these naive ideas of bounding the instantons, instantons from quantum mechanics to field theories, and they failed. The reason they failed was that they forgot that already in quantum mechanics they were cheating, but they got lucky in quantum mechanics. And field theory, they're not so lucky. So we should go back and do the honest analysis of those critical points. So that's what I'm. And I would not be able to do that without Igor, who, well, I will mention because this is where his insight was absolutely crucial. It was one of the stories of serendipity when some conference we were discussing what one's interested in, and he was telling me that he found some solutions of these harmonic maps, but he had the problem that most of his solutions were complex. And I told him that that's exactly what I'm looking for, because we need to classify all complex solutions, because they precisely represent those mind process. By the way, I should say that the first ever algebraic integrable system, which was found actually in the 19th century and is prominently featured in Mumford's paper lectures on Bethe, is a particular case of this problem. It's a certain, even though this is a problem of field theories that have infinite dimensional space of fields, sometimes you can involve some reduction, some special conditions where the problem becomes fine dimensional. So normal system is the system of particles moving on the sphere, also subject to the external oscillator potential, which was famously solved. Tuvalet's talk is a particular case. And was later, much later, realized by Moser to be also on the same. So in the family of Hamiltonians, it is the same problem as the geodesic flow on the ellipsoids, which was studied by Jacobi, which led to Jacobi data functions. And so this is all part of it. So answering Nessa's question, so even though algebraic integral systems seem to be rare in life, they somehow pop up even in these cases. None of us, it's not clear whether a field theories is identical field theories. So, but the fact that the classification of critical points actually has hidden algebraic integrability is a interesting fact, which I don't know algebraic. Okay. So we want to, again, we want to have as many parameters as possible to explore all features of the model, and we want to make them as complex as possible. So my Riemann surface, sigma, will actually be a two-dimensional torus, just T2. With famously adherent to the trigonometry, which is important. I will endow it with a conformal structure, which will actually represent by flat metric, which has two parameters now. One of them is beta, which is a familiar parameter from quantum mechanics, which is basically the imaginary time you travel before you come back. And the new parameter is theta. It's this kind of bend twist parameter. So when your space circle comes back, it's twisted by some parameter. So usually we encode these parameters in the parameter tau, which is essentially theta over 2 pi plus I theta. Right. Now, this program of complexifying everything, but not the whole sheet. So the whole sheet is a real torus, but now I endow it with complex metrics. So tau bar are independent. Tau is an upper half plane, tau bar is a lower half plane, but they don't have to become disconjugates. And in addition, I have this. So this is for the sphere. So the sphere, remember, has so the real sphere has ON symmetry. This complex quadric has ONC symmetry. And in quantum mechanics, I would have inserted the twist element G in the trace, meaning saying that as I evolve some time beta, but now beta is complex because it's parameter of the metric. So as I come back, my field, my target space position is rotated by some group element. This is boundary condition. But what happens in field theory as opposed to quantum mechanics is that it can now impose twisted boundary conditions in space as well. So which leads to different the notion of a twisted field in space. And also it's kind of symmetric. So because I'm working on the torus, the A and B cycle of the torus should be on equal footing. So if I have a twist on one cycle, I should also be able to do a twist on another cycle. So basically, the parameters of the problem are the two complex structures of the torus and the ONC flat connection.
Like when you're talking about the problem, the elliptic genus.
So the elliptic genus has a holomorphic property. It depends only on tau, but not on tau bar. That requires supersymmetry. Here, This is not a supersymmetric
Not so
theory.
it comes to percentage.
It depends on both tau and tau bar, but the whole thing is XL to Z squared. XL to Z acts now both on tau and tau bar. Right. Okay, but that's just, so my background, so my parameters are the flat connection, the group O and C, because of the complexification, and the complexified complex structure of the torus. So this is what replaces the parameters beta, which I had in fluid mechanics, and this background gauge field A. So in terms of the twist, so this now because the fundamental group of the torus is abelian, so my flat connection on the torus is just two commuting elements of ON modular simultaneous conjugation. Conjugation doesn't change anything, just change variables. And so there is a basis where I can kind of block diagonalize my two commuting elements of ON. It's easier to do both. So there are two cases when n is odd even. Yes, here I agree with this formula for the even case. So for even case, you can split your two n-dimensional vector space into two isotropic subspaces, and then this orthogonal rotation will become just rescale as a diagonal matrix one subspace and rescale with the opposite way. And so this is the functional. Eventually, this is the functional which we end up analyzing. So it is quadratic in this field Z and Z tilde, but there is an additional term, which is this last line, U times Z tilde minus 1. So it's the term which involves the constraint. By not studying the maps into the Euclidean space, but we study the maps into the sphere, the complexified. So this constraint is what makes this whole story complicated and interesting. So if I solve the constraint is imposed by the U term. So U times Z tilde Z minus
See U anywhere. Oh, up there. U times Z.
yeah. So U is called Lagrange multiplier. If I vary with respect to U, I get the constraint. I think if I vary with respect to Z, I'll get an equation which involves U. Classical mechanics is called the reaction force. So if you want a particle to move on the sphere, yes, you have to supply a force. But the force depends on where the particle is. In Dennis's favorite Euler equations, the analog of U is the pressure P. It imposes the constraint that the velocity field is divergence free. And in the case of Euler equation, the pressure can be expressed with velocity in no-local fashion. Here, it is similar, not except that here this Lagrange multiplier U is expressed through the fields in local fashions. It's just the derivatives of the Z tilde. So psi vector is just the vector of all Z. So solving. So finding the harmonic maps into the sphere, finding the complexified harmonic maps to the sphere is the same thing as solving the Schrödinger equation. Easy bar. So psi is this vector C1 M, C tilde 1, C tilde L. So every component of psi solves the same equation. M, but so it depends on Z and Z bar. A priori, we don't know how the, so it depends. It is expressed from psi. So this equal to Z psi A bar A. Now Z and Z bar, so it might be a little bit confusing. So d by dz is actually really d by dx plus y. I want to stress that these are all functions of two real variables. There are two coordinates in torus, which are let's say have periodicity 1. And when I write d by dz, what I really mean is the differential operator, which is linear on dx and dy, with complex coefficients. So I think it's then similar for dz r dx y. So we're solving second order differential equation, partial differential equation, variables, with twisted periodic boundary condition. The trivial thing is to find the solutions which such that this vector, so this vector is multiplied by one orthogonal matrix as x shifted by 1, and it's multiplied by another orthogonal matrix is y shifted by 1. So this is called so this is kind of a self-consistent problem. It's a kind of a linear problem. Schrodinger equation is of course linear equation, but this potential u depends quadratically on the solution itself. It's kind of a snake biting its own tail. Remarkably, this problem can be solved. In fact, it can be solved in terms of using algebraic geometry. So we'll get. My God, I did Phillips. Yes, so this is the twist boundary condition, and now so let's proceed. So the trick is the following. First, close your eyes for this equation. Close your eyes. Forget about the relation between u and psi. Just try to think about the general Schrodinger operator. So this function u, the only thing we should know about it is that it's periodic. So u is truly periodic. It's a function of s. So given u, we can associate the kind of an algebra. Well, it's not yet an algebraic, an analytic object. So the block, first the block set, and then the curve. So we should call the term curve. So the block set is the set of Bloch-Elif multipliers A and B, such that your Schrodinger operator has a non-singular solution, such that the twist when x shifted by 1 and the shift and y shifted by 1 are the prescribed numbers A and B. It's a set of, so the fact that psi solves the equation imposes certain constraints on A and B. In fact, it imposes one analytic condition. Turns out that, well, it's a curve, but it's a curve with lots of double points. And so we normalize it. The result is called the Fermi curve. to give you a feeling what it is, let's consider an example. I got carried away when I was drawing. So let's consider an example when the potential U is just a constant. Very simple case. But it's a representative example of Schrödinger operation. Well, when it is constant, we can actually explicitly solve the Schrödinger equation. Solution is just a plain wave, called exponent, something exponential linear function. And you can choose the coefficient of z any way you like. Let's call it k. Then the Schrödinger equation will tell me that the coefficient in front of c bar will have to be u0 over k. So now, given that it's an exponent, I can compute how does exponent transform how does it transform when I go around A or B cycle of the torus. So I'll get this block called here. Well, I think in physics they're called block parameters, and in mathematics these are located block. So these are just exponential functions of k and k inverse. So the solutions are parameterized by k. In different k's I have different solutions. And for each k I can compute the multipliers in B. Because they're expressed in terms of one number k, so there is some relation between A and B. Well, as you can, so what I drew here is I try to embed the line of k's, which is P1, if you add one, into the torus of the multipliers A and B. So this is the picture which I got. What this picture represents, it's meant to represent is that there are infinitely many double points which are labeled by pairs of integers. So there are pairs of k for which you get the same pairs A and B. Because the map from k to A and B involves exponentials, you have two sets of k and k prime such that it needs an exponential zero by 2 pi I times an integer, you get the same multipliers. So if you set the integer for A equals m and for B equals to m, so you have a system of quantizing equations which you can solve. See, k plus u naught over k equals k prime plus u naught over k prime plus 2 pi I m, and k tau plus u naught over k bar equals prime. So prime tau bar. And given, and this is a system of quadratic equations has two solutions. So the solutions means that on the this is my k line. There are pairs of points which the map with A and B will collapse to the center. So this is what I drew. It's kind of a very weakly curve. Infinitely many subdivisions. These actually play a role in condensed matter physics, but see, the normalization of it, yes, it's in genus. What kind of genus persistent solutions for all the points? One of these genera is infinite, but another genus is zero because it's parameterized by k, which is of P1. If I normalize this curve, I get P1, genus zero. Nothing, just so you can see.
A generic fiber of this integral system is not common.
There's no integral system yet. No, I'm just describing one example of a Schrodinger potential, and I'm just saying that there is a curve which can be associated to it, but it's not a spectral curve. I've never said that there was. It's not a spectral curve. It's a curve in a space of local C star systems on the torus, on the two torus we're working on, which is represented by the monodromies of solutions of the equation. Now, what happens? What happens when you now perturb a constant function by a generic Fourier series? If you say let's assume that these coefficients U and N are sufficiently small, is that the double point which is associated with the pair Mn in this way gets resolved. So instead of the local equation of the curve was ZW equals to 0, so it becomes ZW equals to product U of N times U negative and negative. So adding terms to the Schrodinger potential deforms, so actually creates actual genus. So for generic Schrodinger potential, you will get the actual infinite genus unit surface. And there is an interesting subset in the space of all Schrodinger potentials, which is formed by such curves, such potentials for which the curve, the Schrodinger curve, the one which you obtain by normalizing, so by removing on double crossings, is algebraic of finite genus. So these are called algebraic geometric potentials. And so they're rare, but they're dense in the space of all potentials. These are like polynomials from yesterday's story about Lefschetz. Okay. So the remarkable fact, which is the theorem proves to the figure, is that the Schrodinger curves which correspond to the solutions of this equation. So if U is not arbitrary, but such that it comes from solving this equation, they actually algebraic of finite genus. And we published the result for the ON model, which is the model for the sphere. And for the CPN-1, we unfortunately my fault. So we finished the argument just before Igor passed away, but I didn't have time, or really it was difficult to elect myself to write up all the details. But it's actually quite important, because in the physics community there is a certain understanding that the single models with the target space is sphere and single models with the target space the projection space, even though mathematically, well, these are kind of positive recurrent spaces, so the physics should be qualitatively similar. And I believe that it is the case, but physicists consider them as quite different models, because in the late 80s, Zamolochko found a way of characterizing S matrices of integrable field theories, and by his method, the ON model was integrable, so this matrix was two-body factorizable. But when Witten with Goldsmith applied this method to the CPN model, they found that the chronology problem that Zamolochko actually introduced could not be solved. So there was some obstruction. So they conclude that CPN model is not integrable, and therefore they're very different models. But this is the story about the scattering matrix. Scattering happens on infinite space. Here, I'm working on two-dimensional torus, which means that my space is finite, it's a circle. My time is also finite, so I'm not wasting infinite time for things to scatter away. So, technically speaking, it's a different setup, but physically, mentally, it should be the same. These are the same models. So So the fact that the classification of critical points, the Lefschetz thimbles, for the CPN model follows the same pattern as it does for the ON model, suggests that maybe these theories are really same time. Okay, so since everybody started, let me just say maybe only a few words. So we found that one can actually characterize the Fermi curve as an algebraic curve with certain data. It has to have an involution which generalizes the involution k tending to minus k, which we had in this example of the constant potential. And so it has two special points, plus and p minus, where so kind of two infinities, where the solution of this equation, when p plus, so this solution becomes essentially holomorphic, and near p minus becomes underholomorphic. Morphic is defined. So what it means is that if you think about the solution of this equation and you look at the very high frequency modes, so things which are oscillate very wildly, then the potential becomes less, and is less important than the Laplacian. So to Laplacian to annihilate the function in two dimensions, function has to be a sum of the holomorphic and anti-holomorphic function. So so there are these limiting points where this is the two possible behaviors. And then there is a divisor which encodes the information about the twists. So remember, this is this curve. Some special points. So these are the points which contain the information about the special solutions, specific solutions of this equation. So these points, the twists which they represent. So this curve, remember, this curve sits inside. Well, it's a normalization of block set, which sits inside C star cross C star, algebraic torus of the twist parameters. And so this is the divisor which represents those twists which we fixed by the choice of the background Z or C connection. And so there is some data which I will not be very precise about. So these conditions, but so these conditions. So first, I mean, we worked on that for several years, and so first we just tried to find examples of solutions for which we looked for in the place where Igor knew how to look for things, which was the space of algebraic geometric potentials. So first, you assume that the curve is algebraic, then you characterize it. But then we found an argument which shows that actually, so if you have a solution to these equations, then the curve has to be algebraic. And it's a beautiful argument using the ellipticity of this equation and the presence of an infinite number of symmetries which you can act on the space of on these potentials by which are analogous maybe to people who are familiar with the way the Japanese school of Sato and Weaver, Sato actually, generated flow like PZV flows and KP flows. So this story can be generalized to the space of functions of two variables. Treat Z and Z bars as independent variables, and you generate something like KP flows Z and something like KP flows in Z bar. And in fact, you have an infinite number of flows which allow you to generate deformations of this structure together with the logicity, which means that you can only have finite number of solutions, so high dimensional space of solutions, the linearization of this equation implies that there must be some relations between those flows. Again, this old technique of Earnshaw, ancient Krichever, of the commuting differential operators, concludes that there is an algebraic relation, which makes it clear. So I don't pretend. I mean, it would take me a long time to give the argument in full detail. So I will not even start. But that's the outcome. So there is the net result is that following, which is I wanted to explain maybe the fact that there is an algebraic curve underlying the solution. And so this curve comes with its green variety. Remember, it was involution. So the curve in involution can associate some varieties in the Jacobian. Yeah. Anti-invariant. And so this is a abelian variety, which is there. So what's the role of this abelian variety? Well, it turns out that our original two-dimensional torus maps linearly into this abelian variety. So this is the kind of the simplest realization of the picture I had in quantum mechanics, where my critical points corresponded to their we call them geodesics, so they were linear windings, linear periodic windings on the abelian variety. So these were images of S1. And this is now set of two commuting periodic windings, so it's an image of T2 in this abelian variety.
What is the involution of
The evolution was on the curve, So
on the curve?
the curve. So it's a part of the data. It's an evolution which sends k to minus k. So sends
No, but I thought something was anti-invariant.
right. So now you can. So if you think of Jacobian, the way not like think about it, it's a quotient of the first cohomology. So the evolution acts on this cohomology. You can look at the even and odd parts. So I can take the odd part.
So where's that involution come from?
It comes from the fact that my original problem had to do with ON, the orthogonal group. So now if you ask your friend John, so how to classify ON bundles over the elliptic curve, so those would, so you can abelianize the problem, but the line bundles which you get should come in pairs. So there is because of the Weyl symmetry, which inverts eigenvalues. So you have a set of twists A B, you have to have a set of twists A inverse B inverse. So that's an evolution on the modular space of C-star local systems, which preserves the Fermi curve. It has to do with the fact that this operator is formally self-adjoint. That's what we're saying. There is a solution of this equation, there is a solution of psi-star is not complex conjugate, but it has opposite monogamy. Monogamy. So the opposite twist.
Opposite and inverse.
Inverse, right. The logarithm.
Transport.
The logarithm of the logarithm is yes. Same thing as transport because it's orthogonal in orthogonal group. Right. So the explicit solution which you can find for the function and for the potential actually. So the thing is that you can define what's known as Baker-Heiser function. It's some so it's a function which is meromorphic on the curve at the minus p plus and p minus. It has essential similarities at these two special points, and So you can write it in terms of specific theta functions, and the same theta functions will show up in the formula for the potential U. So the argument of this theta function is the point on the spring variety. Dependence on the dependence on the original coordinates x and y in the two-dimensional torus is that we embed this two-dimensional torus linearly with the spring variety and restrict the theta function onto the image. So this is the analog, the two-dimensional analog. I mean, this is so beautiful. Sorry, I speak like better than I castle. But it's just very straightforward generalization of the structure which you see in the quantum mechanics. Okay, so I think I said too much, so let me just say a few concluding remarks. So of course, to ensure that to define the map into whatever given variety, you need to specify the slopes. The slopes are given by some differentials, specific memorphic differentials on the curve. And so to ensure that they have the right periodicity, that you actually close, as x goes to x plus 1 or y goes to y plus 1, becomes another one of these array problems. So to specify, to fix the curve in the family given some periods, the transcendental location. But we found a class of solutions which might be of special interest, for which there's a certain vanishing theory, also certain vanishing theory, the vanishing of the so-called stress tensor and chi and logs, where instead of z bar you have c and z. They actually, these were the original interest figure because these are the solutions which describe which are based on the Virasoro constraints. So people who study, for example, ADS-CFT correspondence, they want to find minimal surfaces in the Lefschetz space and not the de Sitter space, or in the de Sitter space. And let me remind you that all these spaces are just different real slices in my complexified sphere. So one side is described the exhaust. Once I completely classify the critical points for complexified sphere, simultaneously classify the critical points for the Sitter space, or else the Gaussian grid inversion formula. But in string theory, we're interested in not just harmonic maps, but the harmonic maps which obey additional constraints. And those are the constraints which I just mentioned. So we found that in this case, the family curves can be actually characterized in a much more practical way. So they correspond to stationary points of elliptical algebraic model system, which means that those curves can be found in the family of the fine-dimensional algebraic integrable system, and they correspond to a specific Lagrangian subvariety. Again, so this is a nice result, but it's, I don't know the true significance. So the problem which I have not addressed so far was how to select a middle dimensional cycle in the component of the modular space of solutions, which is represented by the abelian brackets. So this problem is present both in quantum mechanics and in the field theory. So that's a problem. I want to point out the analogy of some analogies. People in differential geometry were studying spectral curves for many, many years. So starting with people in the 70s, people became interested in instant dots, gauge theory, and monopole solutions. So one way to study these monopoles, so which are the solutions of the Moivre equation, R3, is to study the twistor curve. And there is some analogy for that for the single models. And so the definition of this twistor curve, one of the definitions which Hitchin proposed, that you study the space of lines in the three real-dimensional space, in the 3D space, which the equation, which looks, I mean, it's not a Schrödinger equation, but it's a kind of it's relative. It's a Dirac equation twisted by the Higgs field as a normalizable solution. So the space of lines in R3 straight lines is actually not explainable. It's a tangent bundle over P1. And so it turns out that the space of lines for which there is a solution is an analytic curve, not algebraic. So the difficulty of using twistor program for monopoles is precisely dealing with this non-algebraic. Well, maybe it's not. Sorry, the curve is algebraic, but the bundle one should study over it. It's analytic, but not algebraic. This is why it's difficult. And then if you replace R3 by R2 cross S1, there's an alternative to the twistor curve, which is the spectral curve. This is so since you have now S1, you can look at the logarithm. So this is there now. Same path of the exponential we discussed before. Now this is the circle space of the complexified connection A plus I5, and the bottom line equations imply that the conjugacy class of this complexified colony varies holomorphically over the remaining two. So that defines the spectral curve, which is different from the twistor curve. This is the curve for which you can apply the usual techniques. It's so what you get here is very similar to the Hitchin system. So something like that might be useful for the problem we have. So the Fermi curves are the analogs of twistor curve, and it would be nice to have more. Now to conclude with something hopeful, something that was hopeful, there's something similar going on in gauge theory. So the ultimate, the actual goal of this whole enterprise was to understand the Lefschetz thimbles for Young-Mills theory in four dimensions. So people believe that Young-Mills theory is similar in many respects to these two-dimensional sequel models on velocity curved spaces. And then this theory works because it describes space you can imagine. So we would like to understand this, but so what I found the analogs of some of these special, very particular solutions of Young-Mills theory, which generalize those periodic windings on the elliptic curve. And these are literally periodic windings on the elliptic curve. So, but this is very special. So what I do, I take Young-Mills theory on R4, but using the conformal invariance, classical Young-Mills Lagrangian, I replace R4 by R1 times S3. You take work on Euclidean space, go to radial coordinates, then divide by R squared. Round measure of S3 times 7. And you can look for special, for the ansatz. So you look for gauge field which has a form. So you take S3 and you embed it with your E group by first identifying S3 with SU2, and then embedding SU2 into your group by the Euclidean homomorphism. And so then take the pullback of the invariant form, G minus dg, and then multiply it by some function of time. This is just a scalar function. And so it turns out that so such gauge fields form an invariant subspace in the space of solutions of Young-Mills equations. And this degree of freedom f, which is the function of time, behaves exactly as an anharmonic potential, anharmonic oscillator. So here is a kinetic term, F dot squared, and there is a double well potential, F squared times 1 minus F squared. It's minimum of F equals to 0 and F equals to 1. So the instanton, which we discussed for the double well potential, which takes an infinite time to go from one minimum to another, is precisely the charge one instanton found by Blank of Schwarz long time ago. So this is the basic instanton solution. I just wrote it in the logarithmic coordinate. But as I explained, there are other solutions which don't take infinite time. So if I replace R1 by a circle, then I can have solutions which will wind around the torus in the space of F and E dot, except that the solutions will be complex. So it will then they will not, so A will not belong to the real algebra of my gauge group, but rather to this complexification, which is what I need for the classification of Lefschetz. So this gives me some solutions of the Lefschetz equation, complex resolution of Lefschetz equation, far from complete. What's really is missing, what is the main obstacle compared to the spherical single models or single models with target space and projection space, is the lack of the global symmetry. I cannot impose twist boundary conditions. So in recent years, people started talking about the general symmetries. One for symmetry. Here, in Yang-Mills theory, we have Yang-Mills theory with gauge group G. There's something called a one-form symmetry. Unfortunately, it's a symmetry taking values in the center of the group. It's very small. It's not continuous. It acts on Wilson line operators. It measures the way the representation of the group in which this Wilson line is evaluated, how it transforms up with respect to the center of the group. So it's not enough to, I don't think it's enough to make contact with this story, but maybe there's somebody can come up with some web idea.
It measures what? Wilson distribution. Just a word.
Yeah, I didn't say the word because it sounds obscene, and I will write it, but it's not, I will write it down. Okay. SUN center is that n is measures what's called the n-arity of the representation. So if you take representation of SUN, you can divide them into n classes depending on how they transform on the direction of Zn. So Zn should act with some character, so there is some character. So now in gauge theory, the representations of the group, they show up in defining the observables associated with loops. So in order to define an observable in gauge theory, I need two ingredients: loop in space-time and a choice of representation. So the symmetry acts on such observables by simply measuring, by specifying the character of the center in that representation. So it doesn't act locally, it acts only along loops. So if one could promote a symmetry into something continuous, then maybe it's similar game. So far, I don't succeed. See, it was this old idea, Polytop, essentially, that topologists, of course, know that connections, gauge fields are functions on the loop space valued in the group. So doing gauge theory in space-time is like doing single model valued in the group whose source is the loop space. So that's why it's important to study single models valued in group length flows or maybe homogeneous spaces, because they kind of model the gauge theory, behavior gauge theory. So if one could play this trick with, but unfortunately, Now Z and Z bar would be coordinates of the loop space. So, well, Big Dow spent a lot of time trying to make sense of Laplace equation of the loop space because it kind of represented those equations. Anyway, so the other problem which what we need to address is to compute the multiplicity. So this is what Dennis was asking me about. So I want to decompose the real slice in the appropriate homology theory as a sum of Lefschetz tables with multiplicities. So these multiplicities, these are formally given by the intersection numbers of the real slice with the conjugate Lefschetz tables. And so even though Dennis says that none of this makes sense, the theory which computes this intersection number might be well defined. It's a could be a non-relativistic version of we don't call it floor theory, but it's something like more in the nature of complexified theory. So it's a theory whose path integral localizes on the solutions of the gradient flow equations and you subject to the boundary conditions that are one. Imagine that you have. So this would be the field theory in one dimension higher than the original problem. For example, quantum mechanics would be two-dimensional theory, for the second model would be three-dimensional theory, for the animals would be five-dimensional theory. So it's formulated on the product of your space-time manifold times the auxiliary line, and you impose boundary conditions that on one end of this line, your fields approach the critical point, one of which are classified, and on the other end, they approach kind of a Lagrangian, which is actually a real slice. So that should define the Ricci problem. And the whole thing localized on the solution of the gradient equation. Kind of a gradient equation, function is a parabolic equation. It's not the Ricci differential equation. So maybe it's more difficult to deal with. But I'm hopeful that this makes sense. So the partition function of that theory with these boundary conditions should be an integer. Then one needs to compute the determinant. So finding the critical points and evaluating the action of those critical points. It's just the first step, step 0. The next step is to approximate the integral of the Lefschetz symbol by a Gaussian integral. That basically means understanding the Hitchin of your function, the critical point. In many examples I looked at, in this quantum mechanical case, these operators, these Hitchin operators, seem to be related to the finite gap Schrödinger operators. So remember that my critical points are linear flows on the Jacobian, on some abelian variety. And so you can associate with this linear flow a potential, Schrödinger potential, which is defined on the circle, but in some analytic continuation to the neighborhood, which is obtained by taking some theta function on this abelian variety, and then restricting it onto the linear trajectory. So U and V as some malformation in that case. So these operators are quite special, and a lot is known about the intelligence. And they seem to represent those Hitchins. So I think it's a nice story which will be completed. A very wild generalization of the story would be to go to string theory. So I was talking about Lefschetz symbols in field theory, in quantum field theory. There's a next level of generalization, string theory, where people believe that classical solutions of string theory, so the critical points of the function which nobody knows, these are two-dimensional conformal field theories, certain conditions. Usually people classify unitary conformal field theories, for which there is a positive spectrum of Isora generators and all kinds of sorts of nice conditions. But I claim that this represents only the critical points which happen to be on real slides. And the true analytic nature of on the field theory and string theory will be revealed once we allow for the complex critical points. So that those should probably correspond to non-unitary conformal field theories. And the Lefschetz tables would be some combinations of them.
I mean, you talked today, you want to give way to generalized string theory to.
Yeah.